Welcome everyone to today's Explainer. I am absolutely thrilled you're here because today we're going on a bit of a hunt. You see, data structures like binary trees give us lightning-fast search times, but only if their internal rules are strictly maintained. If even one single node is out of place, the whole system just breaks. So today, we're acting as algorithmic detectives. Our mission is finding the imposter data hiding deep within our code. Specifically, we're diving into the mechanics of binary search tree validation. Let's get started and catch some rule breakers.
Okay, let's dive into this. At a quick passing glance, this might look like a perfectly normal, neatly organized binary tree, right? But I'm telling you, it's an imposter. If you look closely at the nodes marked in red, specifically node 6 over on the left side and node 7 on the right side, you'll see they are blatant rule breakers. And here's the problem. As trees grow to contain millions of data points, you can't just eyeball them anymore. Without a clear systematic approach, spotting these invalid nodes deep inside a massive data structure is literally like finding a needle in a haystack.
To catch these imposters efficiently, here's our roadmap for today's explainer. First, defining the valid BST. Second, the core intuition. Third, the DFS strategy. Fourth, tracing the call stack. And finally, complexity analysis.
All right, Section 1, defining the valid BST, the rules of the land.
So what makes a valid binary search tree, or BST for short? Well, it's a binary tree where every single node must follow two strict, uncompromising criteria to maintain a legally sorted order. First, a node's left subtree can only contain nodes with values strictly lower than that node's value. And second, its right subtree must contain only nodes with values strictly greater than the node's value. Notice I said strictly. This means absolutely no duplicates are allowed. Every single node has to pass this test.
The really crucial point here is what I like to call the golden rule. For any given node x, right there at the top, absolutely everything in the blue left subtree must be less than x, and absolutely everything in the purple right subtree has to be greater than x. It is so important to remember that it's not just about the immediate left and right children. No, this left is less and right is greater rule applies to the entire subtree, stretching all the way down to the furthest leaf nodes.
Moving on to Section 2, the core intuition, setting the boundaries.
Think of this process like a bounding box, or maybe an invisible fence. As we travel down the tree, parent nodes pass down shrinking invisible fences, a lower bound and an upper bound, to trap invalid values. Let's look at our root node 5. Because it's the root, it can theoretically be any number, right? Between negative and positive infinity? But it dictates that everything to its left must be less than 5. So in checking its left child, node 2, we pass down a strict upper bound of 5. Conversely, everything to the right must be greater than 5, so we pass a lower bound of 5 over to node 7.
And this brilliantly illustrates exactly how our invisible fences work to catch the bad data. Let's look really closely at node 2. It passes down its own rules to its children. Its right child, node 6, naturally gets a lower bound of 2 from its immediate parent. But critically, it inherits the upper bound of 5 all the way from its grandparent, the root node. Node 6 breaks this invisible fence because, obviously, 6 is greater than 5. The upper bound rule was set way up at the top, and the imposter is finally caught.
Next up, Section 3, the DFS strategy, a 4-step action plan.
To do this in code, we're going to use a recursive depth first search, or DFS. This translates into a highly effective 4-step action plan. Step 1. Check if the current node's value falls safely between our lower and upper bounds. If it doesn't, boom, it's an invalid BST. Return false. Step 2. Make a recursive DFS call to the left child, bringing the upper bound down to the current node's value. Step 3. Make a recursive DFS call to the right child, pulling the lower bound up to the current node's value. And Step 4, if both recursive calls pass, return true. Oh, and here's a massive optimization for you. If Step 2 returns false, we stop right there. I mean, there's absolutely no point checking the right side of the tree if the left side is already compromised, right?
All right, Section 4, tracing the call stack, memory in action. Have you ever wondered how recursion actually returns after a deep dive?
Let's actually peel back the curtain and watch the computer's memory in action. We start by placing our first function call for the root node 5 onto the recursive call stack. At this very first level, our boundaries are completely wide open. The lower bound is negative infinity, and the upper bound is positive infinity. Because 5 easily falls between those infinite limits, it passes the test with flying colors.
So, because node 5 passed, our algorithm dives left. Now, we push the evaluation for node 2 onto the top of the stack.
Pay very close attention to what happens to our mathematical boundaries here. The lower bound stays at negative infinity, but look at the upper bound. It gets tightened down to 5, a limit inherited directly from the parent node. Node 2 is safely between negative infinity and 5, so it successfully passes its check too.
We continue our depth-first search, diving left again, and the call stack grows even deeper. We add node 1 to the very top of the stack. Now, its new upper bound drops tightly to 2. We are essentially asking the computer, is node 1 between negative infinity and 2? And yes, it is. It perfectly validates against these incredibly tight new boundaries.
Since node 1 is a leaf node and has no children of its own to check, its job is entirely done. Let's move on and see how this builds, because this is where the invisible magic of recursion happens. The call for node 1 is popped off the top of the stack, and the program naturally falls back to where it left off, which is the call for node 2. Node 2 already finished checking its left side, so now it's time for it to check its right side.
Now, what's really interesting about this slide is that we have reached the climax of our algorithmic detective story. Node 2 calls its right child, node 6, and pushes it onto the stack. The lower bound gets pulled up to 2, but the upper bound remains strictly at 5, remembered perfectly by the call stack's memory from the root node. The algorithm checks, is 6 between 2 and 5? Absolutely not. The logic traps the bad data, and node 6 is caught red-handed.
Because node 6 is a rule breaker, it immediately returns a false verdict. Watch how this false result cascades, bubbling all the way up the tree, condemning node 2 and ultimately condemning the root node 5. Even though nodes 2 and 5 are perfectly valid relative to their immediate children, the entire tree is rendered an invalid BST because of that one single imposter deep in the structure. And by the way, the exact same cascading failure happens when the algorithm encounters that duplicate node 7 on the other side.
Finally, Section 5, Complexity Analysis, Grading Performance. Looking at our algorithm's report card, the time complexity is big O of n, where n represents the total number of nodes in the tree. This makes perfect sense, because in the worst-case scenario where the tree is perfectly valid, we are forced to process every single node recursively exactly once just to be sure. Our space complexity is also big O of n. Why? Well, because of that recursive call stack we just spent time visualizing. If the tree happens to be incredibly lopsided, essentially just a straight line down, the call stack will grow as large as the total height of the tree, consuming memory for every single node all at once.
Which leaves me with a final, fascinating puzzle for you to ponder. If we know that a massively unbalanced, straight-line tree violently spikes our memory usage in a depth-first search because of that growing call stack, how would our memory usage change if we swapped our DFS strategy for a breadth-first search instead? Would scanning horizontally, level by level, save our computer's memory, or would it just create an entirely new set of bottlenecks? Think about it. Thank you so much for joining me on this explainer. Keep asking brilliant questions, and I'll catch you next time.